Hi everybody, today we are learning about scalar and vector projections. So first we're going to learn about scalar projections and then vectors. Okay, so a projection is just a mapping formed by dropping a perpendicular down from a point onto a line. So similar to when we learned the dot product, it's like shining a light on a vector here. Oops. Not recognizing this for some reason. There we go. There we go. It's like shining a light on this, if you can imagine. Shining a light on that, and then taking the shadow of this guy onto here. So if this is vector A, and this is vector B, then the projection of A onto B is how long this is, from 0 until this point. We'll call it N. Okay, so it's like shining a light, and then you get this shadow. So ON here is the projection of A onto B. So if this is theta, that's the angle in between there, then think cos theta is equal to adjacent. So ON, the magnitude of ON, or the length of ON, I guess it's not a vector, divided by the magnitude of A. So therefore, ON, well, you can write it over here, ON is equal to the magnitude of A times cos theta, where theta is the degree, or the angle, sorry, in between A and B. Okay, so it doesn't matter if it's an acute angle or an obtuse angle. Okay, so for here, this can be your B, and this can be your A here, and your projection comes down here, where this is your ON. Okay, now you can think about what is true if this is your B and this is your A, and you're projecting A onto B. Well, you get nothing. ON is 0 in this case. Because there is no projection. Also, you can think about it, the cos of 90 degrees is 0, so that makes sense as well. So if theta is acute, then you have a positive scalar projection. If theta is obtuse, you have a negative scalar projection, okay, because it's going in the negative direction. And if you have perpendicular vectors, then the scalar projection is 0. So it is not possible to take a scalar projection of A onto the 0 vector, since this would result in division by 0, okay, because the magnitude of the 0 vector is 0. So we can come up with another formula. So remember that we know that A dot B is equal to the magnitude of A times the magnitude of B cos theta. So therefore, we can rearrange this. So A times cos theta, okay, so that's this part, and this part is just equal to the dot product of A and B divided by the magnitude of B. So another way of writing the scalar projection of A onto B is the dot product of A and B divided by the magnitude of B. So this is how you can find the scalar projection without knowing the angle between the two vectors. If you know their coordinates, you can do their dot product and divide it by the magnitude of B. So if it's A onto B, notice, I'll use a different color. If it's A onto B, notice that whatever it's onto, that's the magnitude that's in the denominator here. So note that the scalar projection of B onto A is not the same thing. Okay, so a B onto A would be the dot product of B dot A divided by the magnitude of A. So the dot product is the numerator is the same, but your denominators are different, assuming that A and B are not the same magnitude. Okay, so if we went back to this example and did B onto A, it would be like shining a light and dropping down. So we would have to extend A a bit. So B onto A would be like dropping down a perpendicular there. So that would be the scalar projection of B onto A. Okay. Now, one more important thing to notice conceptually is that the projection of A onto B, it doesn't actually matter how long B is. So if you have some like longer A and some short B, it doesn't actually matter how long B is. Okay, you would just, your projection, you just have to extend B, and there you go, there's your O, and this is at a right angle. And let's say you take vectors that are at the exact same angle to each other, but B is like super long this time, and you take the exact same vector A. What you drop down is identical. That scalar projection is identical in both cases, considering that you have the exact same theta here and the exact same A. Okay, so let's just do a simple example here. So for these two vectors, find the scalar projection of A onto B and then B onto A. So for part A, do it over here. Now there's really no notation for scalar projection of A onto B. So I'm just going to go right to A dot B over the magnitude of B. Okay, so we have -3 times -2. Okay, I'm just doing the dot product. Plus 4 times 2 plus 5√3 times -1. Okay, that's a -1 all over the magnitude of B. So that would be square root -2 squared plus 2 squared plus -1 squared. So you get, when you do this, approximately 1.78. So that means if you take this vector A, drop down a perpendicular from it onto B, the length that it would be from the origin to where that perpendicular drops is 1.78 units. Okay, I would invite you to pause the video and try part B on your own, see if you get it right. And then you can check. So B dot A divided by the magnitude of A. Okay, so you get the same thing on the top. Okay, 14 minus 5√3. Because the dot product of B dot A and A dot B is the same. But as a denominator, you get something different, right? You get -3 squared plus 4 squared plus 5√3 all squared. So when you do the math here, you get 0.53. So if you take something from the tip of B, drop it down perpendicular to hit A, the length of that projection is 0.53 units. Okay, so we can expand this a bit to learn about something called direction angles. So direction angles are angles that a vector makes with each axis. Okay, so if you have any vector, just like chilling out here in 3 space, OP, so we'll just kind of draw one. And we'll give it the coordinates A, B, C. There's the origin. Okay, so it makes direction vectors. So it makes, direction angles. So we call this here alpha. That's what it makes with the x-axis. And then it makes some angle with beta with the y-axis. And then some other angle, it's gamma. I'm dotting myself with the z-axis. Okay, so we can use the concepts of projections and dot products to figure this out. So what you're actually doing is projecting OP onto each axis using unit vectors. Okay, so remember, it doesn't matter how long the vector is along here when you're trying to find the angle. So we can just use the unit vectors, I being 1, 0, 0, j being 0, 1, 0, and k being 0, 0, 1. Okay, because since the angle remains the same no matter how long the second vector is. Okay, so that's why we can just use the unit vectors. So let's figure out, well, if you take the dot product of OP and dot it with I, then that gives you the magnitude of OP times the magnitude of I times cos alpha, and that's that alpha that we want to find. So we can rearrange this so that you get cos alpha equals OP dotted with I over the magnitude of OP times the magnitude of I. Well, you know that OP is just, okay, that can be any vector A, B, C, and it's being dotted with 1, 0, 0. All right. Now you know the magnitude of OP is root A squared plus B squared plus C squared. But you know the magnitude of the unit vector is just 1. So what we are left with here, when you dot, I'll do it over here. When you dot these together, you're only left with A. All right? And then here you're left with the denominator A squared plus B squared plus C squared. So if you want to find the angle between OP, any vector, and the x-axis, you just take its x-coordinate and divide it by the magnitude of that vector. Okay, so using the same logic, you could also prove the other two. Okay, so cos beta is just the y value, or b, divided by root A squared plus B squared plus C squared. And then cos of gamma, so what it makes with the z-axis is just c, or the z-coordinate, divided by root A squared plus B squared plus C squared. Okay, so hopefully you wrote those a bit neater than I did there. Those are the three formulas to find the angles. So let's actually do this. Determine the angle that this makes with the x-axis. Okay, so this should be a vector OP. So cos of alpha is just equal to the x value, 2, divided by the length of OP. So the square root of 2 squared plus 1 squared plus 4 squared. So that's just equal to 2 divided by root. Okay, this is 4 plus 1 is 5. 5 plus 16 is root 21. So then you do the inverse cos and you get 64.1 degrees. Okay, if I asked you for the y-axis, it would have been cos beta equals the y-coordinate y1 over root 21, and then you can solve that. Or if I asked you for the angle between that vector and the z-axis, it would be the z-coordinate, or 4, divided by root 21, and then you would do the inverse cos to find those angles. Okay, so that is all I'm doing on scalar projections. Now I'm talking about vector projections. So a vector projection is basically just a vector instead of a scalar. So it's that exact same concept. It's just that we're talking about the vector and not just how long it is, not just the magnitude of that vector. So it's defined by ON, but with an arrow on top. And that's what makes it a vector projection as opposed to just a scalar projection. So it is the vector with the magnitude of the scalar projection, which we just figured out. But it's in the direction of B. Okay? So if this is vector B and this is vector A, then when we shine a light and drop down a perpendicular of A onto B, you get OA n. So ON, just the magnitude of that, is the scalar projection, but ON, the vector with an arrow there, represents the actual vector projection. So the vector projection of A onto B is equal to, okay, so you get the scalar projection of A onto B times the unit vector in the same direction as B. Okay, because it's the length of ON times the magnitude, times the vector that would be on this exact, that would be collinear to this vector. So that makes it, because you're multiplying it by the scalar projection, that makes it the proper length, because a unit vector gives you the right path, kind of, but it makes it only one long, and then you're multiplying it by the scalar projection, which makes it the appropriate length. So this just gives us then A dotted with B over the magnitude of B, which is what we just learned the scalar projection is, times the vector B over magnitude of B, which we learned from last chapter, that is the vector, the unit vector in the direction of B. Now this can be simplified like this. So you can do the dot product over this magnitude squared, and then B like that. Now, I don't really love this form because it doesn't really, I just like using this because I can just remember, okay, it's scalar projection times unit vector, and then that makes sense to me, as opposed to just memorizing a formula. But the reason why they group this together is because when you do all that, you get a scalar from all of this times a vector. So it's that V, that B there, that makes it a vector instead of just a scalar, which is what we were doing before. So I'm just going to do one example, and then we're all set. So find the vector projection of OA onto OB. So let's actually draw this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, -1. Okay, so OA is 1, 2, 3, 4, 1, 2, 3. So there's our vector OA. So we'll say this is A, and it's 4, 3. And then our vector B is 4, -1. And so our our vector projection, okay, you can imagine this coming down at a right angle and hitting somewhere here. So we can put an arrow there. So this O to N is our vector projection. So let's actually go ahead and find it. So remember that the vector projection of O onto B, it's the scalar projection. Okay, so it's A dot B divided by the magnitude of B, so 4, 1. Okay, times the unit vector in the direction of OB. So OB divided by the magnitude of OB. So you can replace this with OA and OB if you want instead. So this is equal to, so dot product is 4 times 4 plus 3 times -1, all divided by, okay, root, so 4 squared plus -1 squared. Okay, that's the scalar projection. And then it's times, so our vector, B, is 4, -1. And then divided by the magnitude of B, which again is 4 squared plus -1 squared. Okay, so from this on the top, you get 13. So 16 minus 3, so 13 over root 17 times the vector 4, -1 over root 17. So what you get is 13 over 17, comma, 4, -1. All right, so now, sorry, just a second. The screen's getting all weird. So now you can just put that through. So 13 times 4 is 52. So you get 52 over 17, comma, -13 over 17. So 52 over 17 is how much? How big is that? Let me see. Just over 3. So 3.06. And then minus 13 over 17. So it makes sense. See, we're just over 3 and just under -1. So that is where n is. That's the vector ON, and that's the scalar projection of A onto B. So I do challenge you. How about you try doing the vector project? Did I say scalar? This is the vector projection because its final form is of the vector, not the scalar. So I do challenge you now. How about you guys try finding the vector projection of B onto A? Okay, and visually you should see that it's correct, and you can take that up tomorrow if you'd like. So thanks for watching, guys. Hope you learned lots.